quickly, I just wanted to, the whole point of this right here is that, now this is the National Electrical Code. It says for theater stages. Now it also pertains to any performance type areas like, anytime you have portable equipment. Now, and this pertains specifically to feeder cable. It says we can use all these different types of cables. Cables have types, and it's stamped on the cable. And the type that we use most often for our shows is type SC. This type right here, that's what we call entertainment cable. And the other type that we see is type W. And what does type W stand for? What is that? What is W for? Anybody know? Not welding, weatherized. It's okay to use cable that's made for outdoor use. It's not okay to use welding cable. Now, a long time ago, there was no type SC cable. So production companies used welding cable because it was the only flexible cable that you could get in 4/0. So all the production companies before 1984 used to use welding cable for feeder cable and Tweco connectors. And then the Olympics came to LA, and one of the local inspectors from the city of Los Angeles noticed that there was a television truck that was being powered using welding cable, and he said, "You can't do that, that's welding cable." And the contractor who installed it said, "But there's no alternative. What would you like for me to use?" And they did a little investigation and found out, yeah, he's right. So the city of LA could either shut down the broadcast of the Olympics or they could allow the use of welding cable. So what they said is, well, you can use it until after the Olympics are over, but after that, no more welding cable. So that's when type SC was developed. That's what we use now. Type SC is what's called extra hard usage cable. That means the jacket can withstand abrasions and cuts. If you lay it on the ground, you can walk on it, and it won't easily break. So that's what we use. But you still see, there are instances where I still see welding cable being used at certain production companies, either because they've had it forever, they continue to use it, or they're misinformed about what they should be using, or for whatever reason. And it still goes on today. So personally, I would never put welding cable into service because as a trained professional, I know better. And if there's an accident, if there's a fire, because welding cable is not rated for continuous duty use. It's got very fine strands. And so if you run it too much, it's going to overheat and it could cause a problem. And if that happens on my watch, then I would have a hand in responsibility. I don't want that liability. So personally, if somebody brought out some feeder cable and I had to do the tie-in, I would refuse. I would send that back, get me some proper cable, type SC or type W. So, something to be aware of. And I mentioned that there are different cable types. This is just for your own use, definition of cable types. You'll see these designations a lot. Type S is extra hard usage cord or extra hard service cord. It's rated up to 600 volts. Cable has a voltage rating, just like it has an ampacity. If you think about, remember this morning we were talking about how water is kind of like electricity. So if you have a garden hose and you connect it to a fire hydrant that has a huge amount of pressure, and you tried you had a nozzle to turn the water on and off, and if that garden hose tried to hold back all that pressure from a fire hydrant, it couldn't do it. It would spring a leak. Well, the same thing would happen if you used 600 volt cable with the 1000 volt service, or if you mismatched the voltage rating of the cable. That jacket, the insulation, is only designed to withstand 600 volts. So you have to look at the voltage rating of the cable just as much as you have to look at the ampacity of the cable. So if you use type SC, that's extra hard usage cable, and it's rated up to 600 volts. So you can use it with 120, with 208, 230, 240, 480 volts, no problem. Okay? Then type SJ is only hard service cord. It's not extra hard. it's hard service cord. What that means is if it's type SJ, and you see it all the time, if you start looking at the cable markings, you'll see, sometimes out in the field, you'll see type SJ cable. What that means is you're not supposed to run it along the floor, because if somebody steps on it, or if somebody runs a forklift over it, it could cause a break in insulation, and now you've got a problem. So type SJ in our world is okay for power cables like this, up to 3 feet long. It's good for breakouts, it's good for twofers, but it's not supposed to be used for any other applications in our industry. That's type SJ. It's good to up to 300 volts. So if you try to use type SJ cable with a 480 volt circuit, that's a problem. Connectors are also, this is an Edison connector. It's what we commonly call an Edison connector. Technically, this is a 515 connector. I think we have the designations later on. This connector is rated up to 125 volts. And what I've seen lately is that some production companies like to take a bunch of LEDs and run them on 208 volts, because that cuts the current in half, so they can put twice as many on one circuit. And so the way they do that is they'll still use an Edison connector, but they set up their power distro so the breakout through the socket apex is actually applying 208 volts instead of 120. Well, when the fixture's all brand new and the cable's brand new, I'm sure it works just fine. But as the thing ages and the insulation breaks down, then it's more and more likely to arc, and arcing leads to heating, and heating leads to more arcing and more heating, and it becomes a vicious cycle until eventually what happens? It melts down and starts a fire, and somebody gets hurt. So use the rating of the connector that's appropriate for the application. According to code, the maximum recommended voltage drop, and I say recommended because it used to say the maximum allowable voltage drop, and they changed the wording. I don't know why that is. But nevertheless, you really should not have more than 3% voltage drop, and that's 3% on the branch circuits or 3% on the feeder cables, no more than a total of 5% voltage drop from the supply to the load. So you can go to the supply, go to the panel, meter the power, meter the voltage there, and then while the gear is working, if you have a twofer to break it out, you can meter the voltage at the load end and do the math and figure out, is it more than 3% or less than 3%? If it's more than 3% drop, then you need to reduce the current or shorten the length of the run or use bigger wire if that's an option. Here are the NEMA connectors. So this basically shows you anything that starts with a 5. So it's a 2-number system. The first number tells you the voltage rating. The second number tells you the amperage rating of a connector. So an Edison connector, I said, is a 515. 5 means that it's good for up to 125 volts, and the 15 is 15 amps. So it's a 15 amp connector up to 125 volts. If you wanted to run these lights at 208, what you need is a 615 connector or a 620 connector. And a lot of times those are locking connectors. So you may have heard the term L620 or an L615 or an L630. That's a twist lock connector. So you plug it in, you twist it, and now it can't easily come undone. I like to use those connectors because they're more secure than, say, a stage pin or an Edison connector, although some of the twist locks don't lock all that well after a while. And a lot of times you see people connect them, twist them, and then gaff tape them. So kind of defeats the purpose. But anyway, so a 6 connector is good for up to 250 volts. If you're doing architectural lighting outside on a building, a lot of times they will use 277 volts, which means now you need a 7 connector. And of course, if you're using 480 volts, you need an 8 connector. So you'll see something like a 730 or a 750 connector or something along those lines. Yeah, question?
Going back to when you were talking about testing the voltage drop when the whole load is on, if the fixture has like a power out, can you test it from there, or would you still recommend having the 2-foot?
Okay, so the question is, if the fixture has power through, can you meter the voltage there at the fixture? If you can get the probes in there, yes, that would be a good place to measure it. I don't know whether or not you can actually fit your probes into a Neutrik PowerCon power through or not. If you can, go for it.
Because I was just talking about like this one, or like,
oh yeah, here we go.
if possible.
Sorry?
If it is possible, because this is like an IEC.
Oh, right. Yeah, so here's an example. You've got power in, power through. So yeah, your probes would probably fit in there. So yes, that's a perfect place to measure it actually. That's not bad. Now here's one with the PowerCon. This is the PowerCon that I was telling you about. So you can see it's designed so that I can disconnect it from the instrument. I can put the instrument in its case, and then I've put the connector in the case as well. So it's not hanging off the fixture. So if I have power through, can I get my probes in there? That would be the white one. I don't know, I'd have to try it and see. I've never tried that before. But if you can, yeah. Yeah, if you can, go for it. I have no problem with that. Now earlier today we were talking about inrush current, and this is just an illustration of that. So what it shows is on the left-hand side. So I was doing a workshop, and somebody asked about inrush current. And specifically, this guy was a motion picture and film guy, and they're used to using those big giant like 10K, 20K Fresnels. And so inrush is a lot more important because they draw more current. That means the inrush current's a lot higher too. So his question was, and he'd always heard, and you may have heard this too, that it's a good idea to preheat the filament on incandescent lamps. So what that means is, instead of turning them all the way off, you leave them at 3%, or before you turn it on to 3%, so that there's just a little bit of current going through the filament to heat it up, to warm it up. Then when you turn the fixture on, you don't get as much inrush current. So he asked if that was true. Should I really do that? And I said, well, why don't we test it out? And so the next day he brought in I think it's a 2K Fresnel, and we hooked it up to my power quality meter, which measures inrush current, and we turned it on 2 different ways. On the left-hand side, we turned it from completely off to completely on. So the filament goes from room temperature to operating temperature like that. And so that's the left-hand side. And what you can see from this is that the inrush current was 120 amps. And the normal current is 14 amps. So it immediately pops up to 120, which is right here, and then it drops down and it levels off at 14 amps. That's with no preheat. Then on the right-hand side, we preheated the filament to 3%. So there's a little bit of current going through the filament, but you can't tell that it's on at all. But then when you turn it on, because the filament's already warm, there's not as high of an inrush. The inrush current was only 30 amps, and then it dropped back down to 16 amps. So you can see that it does have quite a bit of an effect. Now that's for incandescent lamps, which are becoming more and more rare all the time. You know, a couple of years ago at LDI, it'd be the LDI before last. You know, that's the big lighting trade show they have every year. I was doing a workshop there. And a lot of times in my workshops, I like to bring gear and connect it and do all of these kinds of things. And so I wanted to find a tungsten lamp of any sort. Parcan, Alico, Fresnel, you know, just any conventional incandescent lamp. And so I contacted a whole bunch of manufacturers who were going to be exhibiting there. I couldn't find one. Not one manufacturer was bringing conventional lights to show at LDI. And that's because LEDs have gained so much prominence. Arc lamps have gotten better, and so conventional lights. What's the problem with conventional lights? Conventional lights create beautiful light. It's very warm. It renders colors very well, but it's very inefficient. Does anybody know how inefficient incandescent lights are? Like if I have a par can with a 1,000-watt lamp in it, steel beam incandescent lamp with a tungsten filament, what percentage of energy is actually being converted to light? Anybody know?
Regular household bulbs, something like 20%.
Less than 20%. Yeah, regular household bulbs are actually about 3.5%. That means that for every dollar's worth of electricity that I give you, it's only giving me back 3.5 cents worth of light. Does that sound like a fair deal? No, not at all. And the rest turns to what? Heat. So if you live in LA and you're in July, you have, 100,000 watts of light in your church or on your stage, and 97.5% of it, or 96.5% of it is heat. Now what do you have to do? You have to crank up the air conditioner, which costs you even more money. So that's why there's all this move over to LED lights. LEDs are much more efficient, and because of all the push, now the issues that had bothered them, had hindered them in the past, are all but gone. They're flicker free, the color rendering's great, the dimming curve is good, and on down the line. They're bright enough. It used to be that LEDs weren't even, there were indicator lights. That's how weak they were. We used them to, is something on? Oh, look at the LED. Yeah, it's on. That's what we used them for, right? Because they weren't bright enough to light, the stage. But that changed over the years. That all changed, So I think we crossed that threshold. In my mind, it was 2009 when we crossed the threshold from not bright enough to bright enough with LEDs. And I was at a Daughtry show in Austin, and I saw an Elation impression and a Mac 2K, which is an arc lamp, a 1,200 watt arc lamp, and this LED light. And they were both on full at the same time, and to my eye, they were equally bright. And that was the moment I knew that LEDs have arrived. That was 2009, so 6 years ago. And since then, they've just gotten even brighter and better color rendering, better dimming curves, and on down the line. So, I really think that most people would be hard-pressed today to tell the difference between a really good LED light and a conventional tungsten studio light. And here's a test you can do. The next time you're with somebody who's in the lighting business, who knows about lighting. And I love to do this with big famous lighting designers. We'll be at dinner, and I'll say, there'll be like, the first time I did this, there was 3 or 4 of us. One was a college professor, one was a professional lighting designer, and the other 2 were college students that were studying lighting. I said, okay, nobody look up. We're in this restaurant. Nobody look up. Look at the light as it renders on your skin. So are we looking at LED light? Are we looking at some kind of arc light, or are we looking at conventional light? And you know what? Nobody wanted to guess because they didn't want to be wrong, because you can't tell. You can't tell. I was just in Cincinnati at USITT, and we did a panel. We had a big rig like this. First thing we did is, okay, so who here is team blue and black? Who here is team white and gold? You know what I'm talking about?
Stupid dress.
The stupid dress, yeah, of course. Because doesn't lighting have a big part in that? Absolutely. And your eye, the way your eye sees things. My daughter and I were looking at the same picture, and she swore it was white and gold. I was seeing blue and black. What? It's the same picture. How is that possible? Well, think about this. Did you know that 1 out of every 8 males is colorblind? Did you know that? And of the other 7, there's varying degrees of colorblindedness. Some of us have very good color perception. Some of us, not so good. There's a a color test on Facebook going around, match up these, and they had like, 70 or 80, 90 different shades of very, very similar colors. Put them in order of saturation and of hue, And so the lower the score you get, the better your eyes are. The first time I did it, I scored a 17. But I was in a hurry. I had something else to do. I was just like really quickly trying to line them up. And so later on, I came back and said, okay, I'm going to take my time. I'm going to do this. I'm going to get it 100%. I got a 13 the next time. It's really hard to distinguish close colors. So when people say LEDs don't render skin tones or they don't render colors well, you have to wonder how much of that is observation and how much is prejudicial. So it's a fun test to do. Just ask somebody, what are we looking at? Is that LED or is it incandescent or something else? Try it out. Try it out. But now LEDs also have inrush currents because LEDs use a lot of capacitors, and capacitors absorb charge. They store a charge. So when you first turn them on, the capacitors have to charge up. That means you're going to draw a spike of current. And so if you have a big system like this and you turn it all on at one time, you could have quite a bit of inrush current. So you need to be aware of that. So a lot of these moving lights have what they call stagger start circuits in them. What that means is if you have a big rig and you power them all up at one time, they don't all turn on at the same time. They have a random timing circuit or a pseudo-random timing circuit in them. So this one will turn on, then that one, then that one, that. And they all take their turns turning on because by the time the next one turns on, the spike is already gone. And so they don't all hit the line all at the same time. So that's kind of important. I did a class in St. Louis, and the people in the class most of them were from this one theater. And they said that they had a new employee who had worked there for 2 weeks. And the first time he had a day off, his first day off, he brought his girlfriend in because he wanted to show her what he did. He got this new job, first time in theater. And so he took her up to the front of house and he turned on the console. He wanted to turn the lights on the stage. Turned on the console and started raising all the faders. Nothing was happening. The lights weren't coming on. He had all the faders pushed up at full. There's no light on the stage. Then he realized, oh, the master fader's off. So he turned on the master fader and blew up the feeder transformer, $30,000 feeder transformer, poof, up in smoke. She was impressed, let me tell you. So, it's something to be aware of. Just be cognizant of it. Okay, we want to talk about grounding and ground loops. Okay, now so here's an illustration that shows a supply. This is a feeder transformer. This is the black hot. This is the white neutral. And there's two different pieces of gear. This one has the green grounding conductor bonded to it. This one doesn't. There's no green grounding conductor. This could be either a damaged grounding conductor, it could be a lifted ground, or it could be, just made wrong. So if there's a fault, meaning a short circuit to the case, and somebody touches it, then you can see there is a path for fault current that goes through the metal chassis, through the person, through the earth, back to the supply. If there's a fault on this piece of gear, then the path for fault current is through the green grounding conductor, and it's going to trip this circuit breaker and open it up. We already talked about all that. So that's how important that green grounding conductor is. And every piece of metal needs to be connected to a green grounding conductor. So for that very reason, right there. Now, how do ground loops happen? They all happen exactly the same way. If you have any two pieces of gear and they're connected by a signal cable, so we could be talking about, so in this instance, here's our supply, here's one piece of gear, here's another piece of gear. This could be, for example, an audio mixer, and this will be the audio amplifier. And they're connected through this microphone or audio cable. And the audio cable, typically in an audio system, is a 2-wire balanced cable. And then it also has a shield. So here's the 2 wires. The dashed line is the shield and the circle. The circles are the shields also. Now on an audio cable, the shield is always connected to pin 1 on both ends of the cable. And when you plug the cable in, pin 1 connects to the chassis of that piece of gear on both sides. So you have a connection to the chassis on this side through the shield, connection to the chassis on that side. Now, because these are being powered electrically, when you plug in the power cable, the green grounding conductor is also bonded to the chassis. Now you have a complete path for current to flow. The current goes through the green grounding conductor, through the chassis, through pin 1, through the shield, back to pin 1 through the chassis, and over again. There's your complete path for current. All you need now is a voltage, a supply of voltage to cause current to flow in that loop. Where does the voltage come from? The voltage comes from electromagnetic interference. And there's lots and lots of electromagnetic interference in the atmosphere. There's magnetic radiation coming from different sources. Some of the big sources of electromagnetic interference, or EMI, are fluorescent lights. You know, you have a 3-foot tube with a giant arc streaming through it. It's producing a huge amount of EMI. Also, video. Video produces lots of EMI. This video wall back here, and every other video wall, or anything that has video pixels, like these panels, when they turn on and off, they emit electromagnetic radiation. You know, I was doing a show at the Smoothie King Arena in New Orleans, and you know, whenever they have a big event, the phone company wants to make sure, or the producers of the show want to make sure you can tweet it as it's going on, right? So they'll bring the phone company into the arena, and they walk around the arena with this wand checking their signal, and they're looking for signal strength. They have this laptop and this wand, and they're walking the entire arena. They'll walk from, you know, the top level all the way back down the bowl, down to the floor, and when they got to the stage, they were measuring, and they walked by a video wall, and they went, "Whoa, what's that?" You know, and I happened to be standing there. I'm like, "What? What are you talking about?" He goes, "See that big spike right there? There's this big spike of 900 megahertz coming off of the video walls, and there's video everywhere, and every show we do now has tons of video, right? It also comes from current flowing through a feeder cable or through a branch circuit. You know, anytime you have current flowing through a conductor, there's a magnetic field around it. That can induce current into a ground loop like this. So, and there's lots of other sources of electromagnetic radiation in EMI. So if you have a loop like this, then the induced voltage causes current to flow around that loop. And as the current flows, it produces its own magnetic field, which is picked up by the amplifier, and it's amplified, and it sounds like that hum that drives all the audio engineers crazy. And that's how ground loops happen. So how do you fix this? Well, there's a right way to fix it, and there's a wrong way to fix it. The wrong way is to lift the safety ground. You know, they have those 3-prong to 2-prong adapters. We talked about those. Ground lift adapters, they call them. So if you plug that in, and you go from 3 prongs to 2, you just lifted the ground. But that's an unsafe system, so that's not the way to do it. The proper way to do it is to use an audio isolation transformer like this. This is a little device about that big, and you plug the mic cable into one side, and you plug that into the amplifier, the receiving end. So what that does is there's a transformer in here. It's a 1-to-1 transformer. So there's no electrical connection between the input and the output. So the signal gets through, but you've just broken the ground, the loop, and so there's no ground loop current. And that will stop the the noise as well. So that's a proper way to do it. And they have these for video as well, because same thing. You can have a video switcher, video mixer, video, whatever, two pieces of gear, and you can have a ground loop. You can also have a ground loop in a lighting system. If you have say a data splitter, and you have a console, that can cause a ground loop. They're both being powered up. They're both connected to a safety ground, and so that can cause ground loops as well. So that's the proper way to handle a ground loop. Now, earlier we had questions about ground loops. Did we answer your question, Gabriel?
Yeah, I think so.
Okay.
Now, I think it also happens a lot with older buildings.
Yeah.
When you started doing installation and everyone starts talking about how the circuits they have different grounds, so they're not, it's like the main ground is not like the same for all the circuits. So that's also how you get grounded.
So Gabriel says that he's noticed that in a lot of older buildings there are these ground issues, these ground loop issues, and he's absolutely right. Part of that has to do with the effectiveness of the connection, because when you take a grounding electrode and you connect it to the earth and then you connect it to the electrical system, it has a connector on it. Typically the connector has bolts or nuts that you tighten down and it clamps onto something. Over time, the connection degrades and you don't have a good connection to earth. And the other thing that happens is as the cables age and the insulation cracks, then over time that naturally happens, you get more and more inductance, and also the feeder transformer tends to start aging and degrading and emitting more electromagnetic radiation. The oldest theater in the United States, maybe in North America, I'm not sure, is the Walnut in Philadelphia. And I did a little backstage tour over there, and they have lots and lots of these kinds of electrical gremlins, because the wiring there, you walk into the electrical room and you can hear the feeder transformer buzzing, you can feel the heat off of it. So you know that it's got some issues, and it shows up in the audio system. The audio system's kind of noisy. So yeah, as the building gets older, these issues do tend to pop up, and one of the ways you can address them is to redo the grounding connectors and try to separate conductors as much as possible, if that's even possible. Sometimes they're in the same conduit and you can't separate them. But there's other ways to address those issues as well, but they all have to do with lots of money. So, yeah, question?
What does ground loop look like in regards to video?
Okay, what does ground loop look like in video? Well, if it's an older analog system, you get the roll, the frame rolls. In today's digital world, you'll get pixelation. So the picture will break up and it'll pixelate or it'll freeze. Those are all symptoms of a ground loop.
Do they have a meaning with the old analog video systems? I heard of it before. When the ground rolls, they go one direction or the other one. It has a different meaning, like something different is going on.
That I don't know. So Gabriel's asking if in the old analog video systems, if the picture rolls one direction or the other, that there's a different reason for that. I'm not sure about that. I'm not that well versed in the analog video world. All right. Any questions about grounding? 3:11. Let's go ahead and take a 10-minute break.